Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad that you could join us today for our continuing series of webinars about GPS-X. I also have with me today my colleague, Nick Piccolo, who will also be helping me out with the presentation and running some simulations today. We are going to be talking about modeling biological phosphorus removal processes with GPS-X. So this is kind of a sort of the second half of a couple of webinars that we're doing about BNR. So if you go back and look on our YouTube channel, you'll find the previous webinar that we did was about optimizing nitrification and denitrification. So today what we're going to do is we're going to talk about setting up a model to do BioP removal and how our models work and some of the details that you can dig into, and also run some simulations for you as usual. So like always, we would be happy to answer any questions that you have. So in your GoToWebinar dashboard, you will find the questions panel. And so you can enter in questions there. And the way we usually do this is you can enter those in as the presentations are going along, but we will wait until the end of the webinar. So as thoughts come to your mind, please feel free to enter them, and then we'll collect them all up and answer them, as many of them as we can anyway in our allotted time today. And so let's get started. So the plan for today is I'm going to talk a little bit about the background about phosphorus as it's present in wastewater, what the important aspects of it are, and why we want to remove it with wastewater treatment. I'll talk about BioP design, key phosphorus components as we see them in the model, and how the transformations in a activated sludge process are important, how they work, and then how those are represented in the MANTIS-2 biological model in GPS-X. And I'm going to demonstrate a number of things that you can dig into, places that you can find details on certain menus that will help you understand exactly what's going on in each of the zones in your system. And so I'm going to run an A2O process from our GPS-X sample layouts menu. And so we'll dig into the details of what you can find out about looking at the processes as they get solved in the model. My colleague Nick will be doing a presentation on side stream enhanced biological phosphorus removal, S2 EBPR. And so that'll be talking about various types of arrangements of fermentation of the RAS and various other things that will help improve your BioP removal. And we'll also be running some desktop demonstrations and including doing a couple of sensitivity analyses. And so we'll look forward to that towards the end of the presentation today. Okay, so moving on. As you know, phosphorus is an important aspect of biological nutrient removal. It is one of the things that we want to try and get a handle on, and for good reason. So the phosphorus that is leaving the wastewater treatment plant often goes into sensitive receiving bodies of water, where there are often fisheries and other things that are relevant to, or important reasons in that region. So the orthophosphate and other forms of phosphorus that are coming out of the plant are available to be used for growth by plants and animals and mollusks and all sorts of other stuff that you might find in a receiving body of water. So those are important loadings into that receiving body of water. And various things, including industrial activities, agricultural activities, and wastewater itself can certainly deliver a lot of phosphorus to these types of systems. The problem can come in those and when you end up with a situation like this with of eutrophication of your receiving body of water. This is when you have excess nutrients, and in our case, we're talking about phosphorus today, that will allow excess growth of various types of things, including, as shown in this example, algal blooms, which have lots of deleterious effects on these types of things. It can have toxic effects on the water body itself with respect to the other things that are trying to live there. Certainly, if you are feeding a lot of nutrients and you have a significant biomass, bacteria living in that area, it can also deplete the oxygen through a lot of growth. And then you have low oxygen areas, which can have results of things like killing off the fish and so on. So So we all learned a long time ago, many decades ago, that wastewater treatment is important and biological nutrient removal is important because we want to remove the phosphorus in the loading that's coming to the system. In many places in North America, they have reduced over the years the amount of phosphorus that is present in detergents in order to help prevent this problem. But whatever is left over that goes down the drain in the wastewater needs to be dealt with when it gets to the wastewater treatment plant, either through chemical means by precipitating it out or by doing biological activity, which is what we're going to talk about today. So there are a number of different types of biological phosphorus removal designs, plant designs that can be carried out, and there's large numbers of those around the world that do phosphorus removal through the accumulation of the phosphorus in specific phosphorus accumulating organisms. And so this is an A2O process or an AO process that will allow those things to thrive and do the job that we want of removing that. And so we want to be able to use a model to be able to predict that kind of performance, as we do here in our SimuWorks training simulator, understanding how various tank sizes and loadings and recycle rates and internal mixed liquor recycle rates are important to that process. So to be able to explain how we model it, I wanted to start with talking about the phosphorus components as GPS-X sees them, as our biological models see them. So obviously the total phosphorus that we have in the system is made up of a number of different types of components. And the way that these ASM models work is that we do mass balance for each step in the process, like for each reactor, on a number of different forms of phosphorus. And then all of those things might not be able to be measured directly or typically measured directly. So we add them up, and in the end, you come up with something like total phosphorus. But in reality, in the model, total phosphorus is actually made up of soluble P and particulate P. And in fact, these are also broken down into further categories that we actually do predictions on. And so, for example, the soluble phosphorus is made up of soluble orthophosphate and inert organic phosphorus. So that is phosphorus associated with inert COD that you would find in the model. The particulate also breaks down into particulate organic and inorganic phosphorus. The particulate organic phosphorus has a part of it that is associated with the inert COD that floats into and goes through the plant and out the end of the plant without really being affected by the biology. So those are parameters that you can adjust in the influent characterization. We also have, of course, the stuff that's associated with the biomass. We have the poly P, that's the form of the phosphorus that is going to be stored and removed through the bio-P process. And then biomass P, which is really what this is referring to is phosphorus as a nutrient that is taken up for the process of growth, not only by the PAOs, by the phosphorus accumulating organisms, but actually by all of the organisms, all of the biomass in the activated sludge process. Even the regular heterotrophs take up not very much, but a little bit of phosphorus when they do growth of one new unit of COD in the model. And on the inorganic side, we have the various metal phosphates that we would potentially generate if we were doing chemical phosphorus removal. And some of that actually happens even in the biological reactors. You get a little bit of precipitation. But then also, of course, the types of precipitation that you would get with the other inorganic components like calcium and magnesium and potassium and so on, those combining with phosphorus and precipitating out, such as struvite, which is the most common one. And then actually in our model, as I'll show you here in a few moments, there are actually quite a few precipitates that will remove phosphorus from the system. Okay, so what I wanted to hit on was that we actually model all of these things along the bottom here and these ones over here. These are all things that are modeled individually in GPS-X. We do mass balance on each one of those for each of the reactors, and you can predict the concentration of each one of those. And then, of course, we add them all up and we get these other numbers up here as well. So the good thing is when you're doing your modeling, you can actually dig into those details and see those concentrations and put them on graphs and put them in tables and so on and use that information to understand better what's going on in your system. So at any point, any connection point in your GPS-X layout, you can right-click, go to Output Variables, go to the Concentrations menu, and then go to slide down. It's partway down the screen will be your phosphorus variables section. So you'll see here that the orthophosphate, the soluble total phosphorus, the TP. These numbers are all there, and you can drag them onto graphs and do whatever you like. If you click on this more button, you'll get an even, more of the rest of what was on that slide that I just showed you now. Polyphosphates and various other, sums of all of the, particulate total phosphorus, for example. So any of that stuff is available for you to dig into. The other place that you would find it useful too is on the main menu. If you slide down towards the bottom, in the inorganic variables section, amongst all the various inorganic things, you'll note here that we have aluminum phosphate and iron phosphate. Those are the precipitates that will be formed if you're doing chemical phosphorus removal. And then down here at the bottom, here's their struvite down here, magnesium, ammonium phosphate, and there's a few other ones too that we're generating potentially as well. So I'm going to come back to this menu a little bit during my demonstration so that you can see places where we're actually precipitating out struvite. Okay, so we have this phosphorus. We have this soluble orthophosphate that is something that we want to be able to predict in our model and understand how it is going to change and be increased or decreased over time. So in the key processes that we need to capture, the ones that are going on in a wastewater water resource reclamation facility, are, first of all, the required nutrient for the biomass growth. So this is not BioP removal. This is referring to just using phosphorus as a nutrient for just regular growth. We also have the chemical phosphorus removal processes, so precipitating it out with iron or aluminum. And then, of course, we have this thing that we're concentrating on today, which is enhanced biological phosphorus removal, EBPR, or as it's often referred to, luxury uptake of phosphorus, where we are going to grow a specific kind of biomass for the purposes of accumulating as much of that phosphorus as possible in them, and then waste them out into our solids handling facility where we can do various things with it. Okay, so we're doing that in the model, or in our actual wastewater treatment plants and in the model, by growing these PAOs, phosphorus accumulating organisms, and they're the ones that are capable of doing that excess phosphorus storage. And the way that is done is in two steps. First of all, by going into an anaerobic zone, along with enough substrate and other things that it needs. And basically, it's going to release phosphorus while it is storing COD to be able to grow on later. So it's going in that anaerobic zone, you will see a release of phosphorus, a higher soluble ortho-P concentration in that case. And then it's going to move on to an aerobic zone. So in the aerobic zones, it actually will uptake the phosphorus while it is growing on the COD that it previously had stored. So basically what you're trying to do is, just like in this example right here, in this little AO system, in this particular case, anaerobic and oxic. So an aerobic zone allows us to grow them and to have a net removal of phosphorus. So like many other processes, this is dependent on many things. It's dependent on the plant design and SRT and all that sort of thing. One of the other key factors that Nick will be talking about a little bit later on is the COD to P2 total phosphorus ratio in your influent. Is there enough substrate, fermentable substrate there to be able to, have those BioP bugs thrive and grow the way that you want them to. Also the DO and potentially nitrate in the anaerobic zone. That's another thing that we have to keep an eye on and make sure that we're not, accidentally dragging back some nitrate and impacting that anaerobic and making it not really very anaerobic anymore. And then, of course, like any other biological system, there's temperature and pH and so on. And then, of course, the process configuration and sizing and what mixed liquor and SRT are you going to run at and what's your internal mixed liquor recycle. Those kinds of things are pretty well known, and you would enter all of that appropriate information into the model, and it will help predict whether your system is going to work or not. Okay, so what I'm going to do is, now that that's kind of an understanding of the types of processes that we want to capture, I want to talk a little bit about the actual structure of the Mantis 2 model and how we capture that. So just for a refresher, in case you're not familiar, Mantis 2 is our default biological model. This is the model that you will find when you start up GPS-X. It'll start in that comprehensive library. And if you right-click on any one of these objects in GPS-X, you will find that you can go to the models menu and you'll see that we're using the Mantis 2 model. So Mantis 2, which we've been now, is now, I think, 12 or 13 years that we've been using this as our default model. We've had that in development, and we've calibrated it and validated the use of this model over many of our own projects over the years. It is basically originally started as an adaptation of the ASM 2D model. So in that case, you have PAOs, so you have your phosphorus accumulating organisms, and they have a number of growth and decay steps under various types of environmental conditions, aerobic or anaerobic and so on. So there, in the big model matrix, there's many rows to describe the growth and death of those organisms. And you can see that in the rate matrix, we are calculating the PHA storage. And of course, we have fermented substrates such as acetate and propionate that are available there. So there's processes to do that as well. So we also have a two-step denitrification with PAO. So this is now moving beyond what was in ASM 2D. So the phosphorus accumulating organisms do denitrification in an anoxic zone. So I'll be showing you an A2O system in a moment where that will be happening. So that's an advancement. We also have included these inorganic components that are important later on in the digester for the precipitation aspect. So you'll see things like calcium and magnesium and so on. And then we've expanded the way that the kinetics work in the model. So as over the years we've adapted, we've added more components to the model. We've made the model a little bit more sophisticated over the years, and then added the pH model and the gas transfer and other things that are not regularly part of ASM 2D. Okay, so this is the processes that we want to be able to capture into our model. So for each one of these little arrows here, there is one or more equations in the Mantis 2 model to capture that particular rate and calculate how fast that thing is going to happen. So we have to capture the hydrolysis in anaerobic, anoxic, and aerobic conditions. So we have 3 different rates for that. That's basically taking the particulate substrate and hydrolyzing it to soluble substrate. We also have rates for the anaerobic fermentation of that substrate into VFAs. And then the important part, we get on to talking about the actual PAOs themselves. And they have growth in these 3 different conditions, anaerobic, anoxic, and aerobic. And so in those places, we want to be able to have the right amount of phosphorus and COD be taken up and exchanged while those things are happening. So in the anaerobic section here, we want to have the accumulation and storage of substrate as PHA. While that's happening, it is releasing phosphorus. It is releasing ortho-P back into the system. That also happens when the cells are dying as well. So you get that lots of release at the beginning. And then during the aerobic conditions, that is when you're growing, the PAOs are growing on that PHA that has been stored. It takes up at a very sort of excess rate, or that luxury uptake rate that is referred to, taking up that ortho-P and then storing it as polyphosphate. So basically what's happening is you are storing the PHAs first, and then in the aerobic conditions, you grow on that PHA and you take up all of that stuff that you released plus more. So it is a way to, it is sort of a net gain of phosphorus into the PAOs, which you then settle out in your clarifier and then remove from the system before the effluent goes out. So that is how BioP works, and we need to be able to capture those 3 or 4 steps in that process. So the good news is that's all built into Mantis 2 model, and when you run your system and you solve the model, you can see all of those individual steps in the process individually from each other. I think this is one of the menus that maybe doesn't get quite used as much as it could be. Maybe it's not a particular menu that you're familiar with, so I wanted to show that today. You right-click on any one of the biological tanks and go to the Output Variables menu and go to the Mantis 2 Rates menu. The top part of that menu is basically all of the biological steps in the process. And you can see their rate as these things are happening. So this is milligrams per liter per day, right? It's a rate at how fast these things are happening. So it's really good, useful information to be able to see. Like say your BioP system's maybe not working quite the way you want to. you could take a look here and see what is the relative size of these rates compared to each other. So I grabbed part of this results from the aerobic tank here. So you can see under aerobic conditions, we would expect to see these two items here be the highest number. These things are happening a couple of order of magnitude faster than all of the other processes that are shown here. So that makes sense, right? These are aerobic growth. So we're growing those new PAO bugs on that stored PHA, and it's taking up the phosphorus while it's doing that. So those are good. That's the actual BioP process happening here. These anoxic processes are not really happening at any significant rate here. So that's what we would expect, and you would like to be able to go here and be able to look at these things in order to help understand and make sure that you've got your design set the way that you want it to be. So just as another different example of that same thing, here's the anaerobic digester. Right-click, go to the output variables, Mantis 2 rates menu, and you can see what is being precipitated in my digester. And you can see there's mostly insignificant numbers here, except for this one, which of course is the struvite precipitation. Okay, so those are things that are kind of handy in order for you to be able to dig around and understand what's going on in your system. So what I want to do now is actually run some desktop demonstrations for you. And I'm going to use one of the example layouts that comes with GPS-X. When you install GPS-X on your computer, you get about 100 layouts that have already been put together for you. And you can load them up and use them as they are, or make them sort of, adapt them, save them to a new name, and make them the beginning point of something that you're going to be working on. I'm going to do the A2O process. What you can do is go to the File menu, go to the Sample Layouts menu. It brings up this thing, and then select, for today's talk, we're talking about biological phosphorus removal. You can see all of the different plants that we've already put together for you. Okay, so I'm going to talk about the A2O process. So just to refresh your memory, it's an anaerobic tank, an anoxic tank, and an aerated aerobic tank. And these are there with a recycle that comes from the aerated tank back to the head of the anoxic zone. And so what we want to do is just show you where you can play around and dig into some of the details, seeing where that big phosphorus release happens and where the big phosphorus uptake happens in these particular tanks. Right. Okay, so let me flip over to GPS-X. Here we go. So here's our anaerobic tank, here's our anoxic tank, here's our aerobic tank, there's our internal mixed liquor recycle, this is the RAS, and all the rest of the sludge that's coming off of the primary and secondary clarifiers is being taken over here to this thickening, a little bit of sludge pre-treatment. This is really just doing a little bit of hydrolysis on it before it goes into the digester to increase the gas production. So in the digester, and then we do dewatering, and then it's hauled away as sludge. So we hope that most of the phosphorus that comes in the front of the plant will go out through the sludge. That's what we want, as opposed to going out the effluent. Okay, so I'm going to run just a steady state solution here. Let's poke around, take a look at some of the numbers, just so that we can see what there is to see about this particular system. So if I start here, I'm just going to double click on this anaerobic tank here. And one of the things that you can do, I don't know if you've ever played around with this menu at the top here, but right now this is showing the flows going here. You can actually display other things on this upper top here. So one thing I want to do is display the soluble phosphorus. And that shows us for each one of these connection points what the phosphorus is going in and out of this unit. So here we can see coming in soluble phosphorus is coming in at 11. The amount coming back through the RAS, of course, this is after the BioP. It's being recycled back, so of course it's low. It's 0.2. But you can see leaving, it's 35. That means this is the tank where we're seeing that P release because this is the anaerobic tank. So you can see a lot of, just read into, an understanding of what's going on in your BioP system just by plotting and putting the right things on this menu here. Of course, you can read some of that same information down here as well. But yeah, definitely we got a lot of P release in all of that biomass that's being recycled back from the secondary clarifier. Okay, so now we're moving on to the anoxic tank. I'm going to do the same thing here. Let's go back here, and we can see that there's our 35, almost 36 milligrams per liter of soluble phosphorus coming in. And of course, we have this internal mixed liquor recycle of next to nothing coming in. So you can see that it's approximately diluted by half, right? So there's not a significant amount of BioP release or uptake going on in here because this is an anoxic tank. It's not anaerobic because that that internal recycle coming back is going to have lots of nitrate in it. So it's not an anaerobic zone. And then we're going to move on to the aerated zone. This is where all the major business is happening with respect to removal. I'm going to go back down here. We can see 18 coming in and all the way down to 0.2 on the way out, right? So that is that luxury uptake. It's growing a lot of PAO bugs, those heterotrophs, and they're taking it up, growing on that PHA and taking all that polyphosphate with it. So there's your actual information that you can dig out of just looking at it this way. And as I mentioned before, you can actually just right-click here, go to this Mantis 2 rates, and in the top of this menu, this is, as I was saying, you can see all of the different steps in the activated sludge process. From, just doing all of the regular activated sludge steps, so, hydrolysis and growth and death and so on. They're all here, and these numbers are really useful to kind of sort of see what are the significant, you sort of comparing relative to each other, what are the most significant things going on in this anaerobic zone here. So we can see there's lots of decay of heterotrophs going on because there's no air, for example. So if we slide down here, past the AOBs and NOBs, which aren't doing anything in this tank. Then here we go, storage of PHA by our BioP bugs using acetate and using propionate. Here, there's where that storage of the PHA is going on. Okay, so now let's look at that same one over in the aerobic zone. So that same menu, let's slide back down to that same spot. Okay, now we're in an aerobic environment, so that storage is not happening, and in fact, it's the aerobic growth ones that are happening. These are the big numbers in this particular tank, and we can see that it's uptaking, storing all of that polyphosphate, getting rid of the phosphorus that we want to get rid of out of our system and storing it in the bugs before they get wasted. And just for fun, I'll also mention down here the digester. I talked about that earlier as well. If we go in here, we can see, of course, nothing happening much on the growth side here. We can see there's a lot of, hydrolysis happening because it's an anaerobic environment. So let's slide down here into our section. No growth of BioP bugs of any kind. There's decay going on of our bugs. However, if I get to the precipitation section, here's their struvite, there's that big number. So that's what's happening. We're precipitating it out as well. So sometimes when I'm working on these types of, somewhat complicated activated sludge systems, especially when you got 2, 3, or 4 or 5 different kinds of biomass going on, and you really want to dig in and understand, maybe I can see a concentration coming in and a concentration going out, but it's not telling me the whole story. Going to that Mantis 2 rates menu is really useful, even if you don't know the absolute number that you need, but you can see relative to other rates, which is the most important thing happening in that particular unit. Okay, so that tells me mostly what I wanted to see. One last thing I would like to just give a shout out to is our Sankey menu. This is another place where you can get, it's the same information, but just visualized in a different way. So here, Sankey diagram, for those who might not have ever used this before, is basically a visual representation of the flow of something in a system. So in this case, it's the flow of the water, and the thickness of the line is proportional to the value in that particular connection point of the model. So here, this is just flow through the system, 2,000 meters cubed a day coming in. Of course, this is where most of it is happening. A lot of flow is moving around in the recycles and so on. And it goes all the way out. And then, of course, the small amount of flow moves through the solids handling side. Now, the part that makes it useful for looking at BioP is to come up here and click on total phosphorus. So now we're dealing with a mass flow of the phosphorus. This is total phosphorus, including all the forms, so both the soluble and the particulate. And we can see here coming in, we have 24 kilograms per day of phosphorus coming into this system. And it goes through the BioP system when we're gathering up quite a lot of that, moving it through, concentrating it into the system down here. This is the solids handling system that I mentioned earlier. So it's coming down here, goes through that mechanical. We're sending a lot of this back to the head of the plant, as you can see over here. goes through this hydrolysis unit. You can see it actually doesn't make any change to the phosphorus at all. Really, it's just breaking down some COD. And then it gets collected, dewatered. Some of that goes back to the head of the plant as well. And then most of it goes out in the sludge, which is what we want. So you can see here, of that 24 that comes in the front end of the plant, 1.5 goes out the effluent and 22.5 goes out through the sludge. So that's our looking at the relative efficiency of the capture of all of the phosphorus. A Sankey diagram that does that super nicely. You can see the relative balance of this versus this. And so anyway, just a nice way to sort of mass balance the numbers and visualize it in a slightly different way. So Sankey diagrams found here under this eyeball visualization button. Right, okay, so I'm going to head back to the slides now, and I'm going to invite in my colleague, Nick, who's going to be talking about, like, all the stuff I was talking about was the mainstream BioP removal, and I'm going to let Nick focus on talking about the side stream removal. So Nick, I'm going to switch you over, make you the presenter right now, and you can jump on in.
All right, thanks, Spencer. So the next thing that we wanted to talk about, as Spencer said, is a little bit just about the side stream EBPR and how it's modeled in GPS-X. So side stream, or S2 EBPR, is kind of an emerging or kind of hot area of research that we just wanted to discuss a bit. Just for those who aren't very familiar with what side stream EBPR actually is, it basically consists of just modifying an existing EBPR process by diverting a portion or all of the RAS or anaerobic MLSS to an anaerobic side stream reactor. So for this side stream reactor, there's no influent or primary effluent wastewater fed to it, and eventually after a fairly short, usually HRT, the flow from the side stream reactor is returned back to the mainstream process. Now, the reason that this is interesting is because S2 EBPR or side stream EBPR strategies have been implemented in a lot of real-world facilities and have been shown to improve phosphorus removal versus EBPR systems. But as to why it improves performance, there's right now, I guess, a lot of discussion and many theories about that. But in general, the main idea is that S2 EBPR leads to less variability in the substrate available for EBPR, basically because there's an increased or enhanced fermentation in the side stream reactor. So, basically, just to expand on that, there's a lot of phosphorus release and PHA uptake in the anaerobic zone, and that's less dependent on the influent readily biodegradable COD to total phosphorus ratio. When you use an S2 EBPR configuration, because there's now fermentation happening in the side stream reactor, that's supplementing the biodegradable COD. So this image that you see on the slide here is just a screen grab of the front page of the WRF side stream EBPR report that came out in 2019. And this report detailed 4 different types of side stream EBPR. So I'm just going to briefly explain what those are. First, there's the side stream ROS fermentation. So this is where a side stream reactor is added to the ROS stream, and about 5 to 30% of the ROS is diverted to that reactor, typically with an HRT anywhere between 16 to 48 hours. The next one you can see here is the side stream ROS fermentation with supplemental carbon addition. So this is very similar to the first one, except now 100% of the ROS is typically sent to the side stream reactor, but the HRT of the reactor is much shorter. So it's around 1 to 4 hours in this reactor, and they're adding some supplemental carbon. So that could be some carbon from a primary sludge fermenter or just some methanol or acetate. The next one here is side stream MLSS fermentation. So in this case, instead of the side stream reactor being on the ROS line, they're actually putting a side stream reactor that they're pumping some of the MLSS to, and it's usually around 5 to 15% of the anaerobic zone MLSS that they divert to this reactor. And in this reactor, they try to have a pretty low mixing or almost no mixing at all to decouple the HRT and SRT. So basically, they're trying to grow a bunch of fermenters in this reactor that stay in there for a longer time. And then finally here we have the unmixed inline fermentation. This is very similar to the last one, the side stream MLSS fermentation, except in this case, rather than it being in a side stream reactor, they just try to decouple the HRT and SRT by slowing down or turning off the mixing in the mainstream anaerobic zone. So it's not actually a side stream configuration physically, but researchers mostly agree that it's probably kind of governed by the same mechanisms that are observed in the side stream tanks. So the thing is that this report, I guess, it kind of suggested that current models are not really able to EBPR performance compared to just the typical EBPR performance. So what we wanted to do is kind of look into this. So we implemented these 4 configurations on the slide here in GPS-X and compared their performance versus the performance of just the typical Bardenfo process, with the objective of evaluating whether current models can predict side stream process performance. All right, so now I'm just going to briefly show how we set up all these layouts in GPS-X. So you can see here, this is the side stream Ross fermentation layout. So it's just a typical Bardenfo process, and I've added a Ross fermenter to the Ross line, and we're diverting 30% of the Ross to that tank, and the HRT in that tank is 48 hours. This next layout here is the side stream Ross fermentation with supplemental carbon addition. So here it's very similar, obviously, to the layout I just showed, but now we're diverting 100% of the Ross to this tank, and we've lowered the HRT to just 4 hours. As well, we're also adding some acetic and propionic acid mixture at a ratio of 3.3 grams of COD per gram of phosphorus in the influent. This next one here is a side stream MLSS fermentation. So now I've added the tank just after the anaerobic zone of the mainstream process rather than to the Ross line, and I'm diverting 15% of the MLSS to this tank. And you can see I have this highlighted clarifier object here. I'm just using this with an empirical solid separation model to raise the SRT. So basically I'm just using it to send some solids back to that tank so that we can achieve that decoupling of HRT and SRT in the side stream MLSS fermentation tank. All right, and then here's the final one. It's unmixed inline fermentation. So it's similar to the one I just showed, except now I'm just adding this clarifier to the actual mainstream process, just to send some of that solids back to the anaerobic zone to decouple the SRT and HRT in the anaerobic zone. Okay. So on this slide, we have the results of the analysis that I ran. So basically what I did was I ran steady state simulations using the 4 layouts that I just showed, as well as just an unaltered Bardenfo process layout. And each simulation had the same influent conditions, so an influent total phosphorus of 8.5 milligrams per liter and a soluble or orthophosphate of 6.8 milligrams of phosphorus per liter. As well as the same influent readily biodegradable COD to total phosphorus ratio of 15 grams of COD per grams of phosphorus. Okay, so this graph here basically just summarizes the results. The dark orange line represents the total phosphorus in the effluent of the simulated plant, and the light orange line represents the ortho-P in the effluent. So looking at the results, we can immediately see that using a side stream process does improve the total and soluble phosphorus removal compared to just using the typical EBPR Bardenfo process. And we can also see that the improvement is in the same magnitude as the improvements reported in the WRF report. So here I just have a screen grab from the WRF report where they're showing some actual data from a plant, the total phosphorus in and out, and the soluble phosphorus or the ortho-P in and out for a plant that switched from using EBPR to side stream EBPR. And you can see that the ortho-P in the effluent goes from 0.4 in the EBPR process to around 0.1 in the side stream EBPR process. And with GPS-X, we're seeing the ortho-P go from 0.2 to around 0.05. So in both cases, we're seeing a 75% improvement in the orthophosphate removal. So what we can basically say from this is that we can comfortably or be comfortable with the fact that GPS-X is predicting improved performance with the side stream configurations. So for design purposes, it doesn't really seem like it may be necessary to add anything to the model, contrary to what the WRF report was suggesting. Okay, so now I'm just going to run a couple sensitivity analyses just to show S2 EBPR in action in GPS-X. So first, I'm just going to run these first two sensitivity analyses on the side stream tank volume and on the influent readily biodegradable COD to total phosphorus ratio, both with and without a side stream tank. Then I'm going to jump back to the slides briefly before running the third analysis. Okay, so here I just have a typical 5-stage Bardenfo process layout with a side stream tank that I've added over here. And I'm going to use this to run those sensitivity analysis I just said. So the first one on increasing the size of the side stream tank, so basically turning this Bardenfo process into an S2 EBPR process, and then on increasing the readily biodegradable COD to total phosphorus ratio for both a typical EBPR process and an S2 EBPR process. And then I'm going to go back to the slides before coming back and running the final analysis on oxygen penetration in the anaerobic zone of an EBPR process. Okay, so for the first sensitivity analysis, I'm going to be, as I said, converting just a conventional Bardenfo process into an S2 EBPR process by incrementally increasing the size of the side stream reactor. So here you can see I have the side stream maximum volume, and I have the variable set up as an analyzed step variable. So it's going to step from 0 to 300 meters cubed at a delta of 60. So I'm just going to start running that now. And while this runs, I'll just explain the graphs I have here. So first, I just have the effluent phosphorus graph. It's fairly self-explanatory. There's a total phosphorus and the orthophosphate on this are going to be displayed on this figure. And then here I have some of the mainstream anaerobic zone rates. So this is actually showing some of the things that Spencer was showing in those menus, just those Mantis 2 rate menus. I've just put the hydrolysis rate, the fermenter growth rate, and the PHA storage rate from the mainstream anaerobic zone here, just so we can visualize it a bit easier. And then here I have the DO concentration in the anaerobic zone. It's not really important until the last sensitivity analysis, so we'll get back to it then. And then here's the side stream reactor HRT. So it's just showing as the volume increases, how the HRT in the side stream reactor is increasing. Okay, so looking at the results here, it's basically as we would expect. The total and orthophosphate concentrations are decreasing as we're increasing the size of the side stream reactor. And then obviously we're seeing that increase in the side stream reactor HRT. With the anaerobic zone rates, there's not a whole lot of change here, but we do see a slight drop off in the hydrolysis and fermentation. So that's the red and blue lines. Just this is because some of those processes are now actually happening in the side stream reactor. So there's not as much of an onus on the anaerobic zone to take up all or to play that role. And we also see a slight increase in the PHA storage using VFAs. And this is basically just because the side stream reactor is obviously having some fermentation happening in it and producing substrate for PHA storage. Okay, so now I'm going to move on to varying the influent readily biodegradable soluble substrate to total phosphorus ratio. So I'm just going to switch now the readily biodegradable COD over P ratio as the analyzed step variable. And we're going to be varying this between 13 grams of COD per grams phosphorus to 23 grams of COD per grams phosphorus. So this is a pretty wide range, and this 13 here is a pretty undesirable constant or ratio for BioP, but when we get into 23, it kind of gets into the more reasonable range for where we expect BioP to happen. And the way that we're going to be increasing the ratio is just using a mixture of acetate and propionate. Okay, so we'll just let this run. All right, so we can see already what's happening is basically what we would expect. The total and orthophosphorus concentrations are decreasing as we increase the readily biodegradable COD. And this result's going to become a bit more interesting when we compare it to the profile for the next sensitivity analysis, where I'm actually going to be using a side stream tank. In this sensitivity analysis, I don't know if I actually mentioned that, but there's no side stream tank here. So this is just the conventional EBPR process. We also see a strong increase in the PHA storage rate here. So this is obviously what we would expect, as we're just adding soluble substrate, namely the acetate and the propionate, which can just be very easily uptaked by the POWs in the anaerobic zone. Okay, so now I'm just going to switch this to an S2 EBPR layout by adding some volume to this side stream tank. So now there's a 300 meters cubed S2 EBPR tank there. And I'll just run it again. And I'm also just going to bring up a screen grab that I took earlier that shows the results from the non-S2 EBPR graph, just to highlight the differences between the two situations. So basically, we see what we would expect, which is that GPS-X is predicting that with the S2 EBPR configuration, we're starting at a lower effluent phosphorus concentration, even at the very low RBCOD over P ratio, and it gets down to very low effluent phosphorus concentrations a little bit earlier than the non-S2 EBPR layout does. So this basically just shows, as we already saw, that using GPS-X with S2 EBPR configurations does make a difference, and the models seem to be able to predict the improved phosphorus removal when we use an S2 EBPR layout. So now I'm just going to briefly jump back to the slides to show the results of a sensitivity analysis that kind of ties into the one I just showed. So here I just ran basically a similar analysis to the one I just showed in GPS-X using the 5 layouts from before, from that previous example that I had showed where I compared it to the WRF report. So just those 4 S2 EBPR layouts and the Bardensfo process. And here I evaluated the same thing I just showed, just changing how seeing how changing the influent readily biodegradable COD to total phosphorus ratio affects the effluent phosphorus concentrations for the different side stream configurations and the Bardensfo process. So we have the total phosphorus graph there on the left and the orthophosphorus graph on the right. And the main takeaway from these graphs is that in general, if you use any side stream configuration, it's going to lead to a bit more successful biological phosphorus removal than if you use a non-side stream configuration like the Bardensfo process. And these successful phosphorus removal can be achieved at a lower readily biodegradable COD to total phosphorus ratio. So the black line is the Bardensfo process results, and all of the colored lines are the different side stream processes. And you can see that they're all shifted to the left, which basically just shows that any side stream configuration can be viable at a lower influent readily biodegradable COD to total phosphorus ratio. And it's also shifted down a bit. So even at the very high ratios, the side stream processes are actually able to remove a bit more phosphorus than just the Bardensfo process can. So this method of sensitivity analysis has a wide-ranging applicability. Like you could just use it just to assess just a Bardensfo plant design, or even if you were trying to upgrade a plant, you could throw in a couple different reactors, try a couple different scenarios, and see which S2 EBPR formulation is going to give you the best results. Okay, so now I'm just going to quickly jump back to GPS-X to just go over my final sensitivity analysis, in which I'm going to be varying a parameter that we have in GPS-X called the gas mass transfer coefficient at surface. So this is basically just a parameter that we can vary to basically look at the effect of the strictness of an anaerobic condition on EBPR performance. Because as we increase this coefficient, we basically are just allowing oxygen to slowly seep into the system. So I'm just going to run this now. And basically what we can already start seeing is as the coefficient is increasing, we're seeing the effluent phosphorus concentrations increase as well. We're also seeing, obviously, the DO in the anaerobic zone is increasing. And we can see that even though like the scale on this graph here only goes up to 0.1 milligrams of oxygen per liter, and the line only really gets up to around 0.04. So at the worst here, we're having a very, very small dissolved oxygen concentration in the anaerobic zone, but you can see the very significant effect that it has on the total EBPR performance. This is also shown by the very strong decrease in the PHA storage in the mainstream anaerobic zone. And this is basically just because now that there's a little bit of oxygen there, some of that soluble substrate is able to be taken up by heterotrophs instead of just the PAOs. So now some of the VFA isn't available for PHA accumulation. Instead, it's going to heterotrophic growth. So yeah, basically this analysis just kind of shows that there's some very negative outcomes to having even just a little bit of dissolved oxygen in the anaerobic zone. And it kind of shows that our Mantis 2 model and just most typical BioP models in general are already accounting for the kind of deep ORP conditions that they expect in those side stream reactors with mechanisms like this, where you can just see the effect of just a tiny bit of DO on the EBPR performance. Okay, so I'm just going to jump back to the slides. And just going to briefly summarize this S2 EBPR discussion. So basically, the main takeaway is that GPS-X does predict improved EBPR performance when we use side stream configurations. And here on the slide, we just have some possible explanations for this improvement. So firstly, there's an improved hydrolysis that results from the longer overall anaerobic HRT, and this provides more substrate for the fermenters. So the fermentation is also improved, obviously, with this longer anaerobic HRT, but since hydrolysis is typically rate limiting, the overall process improvements are probably limited by the improvement in the hydrolysis. Secondly, with the extended anaerobic zone comes greater nitrate and oxygen removal. So basically, there's a lower concentration of electron acceptors in the mainstream anaerobic zone, and this reduces the ORP and improves fermentation. Furthermore, the presence of nitrates and oxygen also stimulate unwanted competition with the PAOs from the ordinary heterotrophic organisms. So those take up a portion of the VFAs that would ideally be used for PHA accumulation if there's any nitrates or oxygen present in the system. So the WRF report that we mentioned earlier does offer some additional explanations for the improved performance of the side stream configurations compared to the typical BioP setups. Firstly, there's some preliminary research that has suggested that there's a certain PAO called tetrasphaera that can obtain energy for growth via fermentation at very deep ORP, so low DO conditions in the side stream reactors. Secondly, some researchers believe that at these very low ORP conditions in the side stream reactors, PAO growth is actually favored over GAO growth. But the report does stress that more research is necessary to really nail down the significance of the contributions of these mechanisms, because it's still kind of up in the air exactly what's going on in the side stream reactor. So we're currently evaluating these the contributions of these mechanisms from a modeling point of view, but we're pretty happy with the current model because, as we saw, it is able to produce the results that we expect, namely the improved performance when we add a side stream configuration to a conventional EBPR configuration. And the current model structure already contains mechanisms that explain that improved performance, namely the improved hydrolysis and the very strong effect of just the tiny amount of dissolved oxygen on the EBPR performance. All right. So now I'm going to send it back to Spencer to just give some final thoughts on the presentation.
Thank you very much, Nick. I am going to just wind up the webinar here with a few final thoughts about the entire discussion today around modeling biological phosphorus removal. So our Mantis 2 biological model, is set up to do exactly that. It effectively simulates the important processes that you get when you're trying to grow biomass, the PAOs, their growth and decay under various different kinds of circumstances, the phosphorus release, the PHA storage, the uptake, the luxury uptake, all of that is already captured into the Mantis 2 model. As I mentioned before, the individual process rates, the individual steps in that process can sometimes be really enlightening and really interesting to take a look at when you're looking at your design. If it's maybe not working as efficiently as you would like, you could take a look and dig through those process rate menus and see which things are happening where. Maybe there's an opportunity to make your anoxic tank a little bigger or what have you. You can try and optimize those processes there. And lastly, that as Nick demonstrated, the side stream eBPR is modeled actually quite well by our Mantis 2 model in all of those various configurations, and the model is sensitive to the things that it should be, such as the intrusion of oxygen through the surface of that tank. So